With us, Spela Spenko. She is currently affiliated with the University of Bruxelles at Belgium, and she will be talking about HMS Symmetries and hypergeometric system. So this is quite a newly evolving concept in the area of algebraic geometry and algebraic varieties. So Spela will enlighten us about HMS Symmetry. Welcome, Spela, and thank you very much. So welcome, Spela, for this particular panel. Over to you, sir.
Thank you very much. So it has been really nice to be here for the last 2 weeks. Is it okay?
You want mic?
Is it I need it or
For this.
okay?
You just keep talking on
Okay. I just continue or?
Yeah, you just
Okay. Yeah, so as said, I will talk about homological mirror symmetries.
I'll carry this. Guess we had elements.
Is it not too loud? Sure. Okay. Yes, but let us first start with classical symmetries.
Click on the screen.
And now see. No, not this one. All right. Is it working? Yeah. No. Oh, that should work. Maybe the budget have some issue.
That's an interesting stuff, but that's okay.
Yeah, it worked.
Okay, so let's start with classical symmetries. So here we have a photo of K2, and we would like to find its symmetries. So what kind of symmetries does this picture have? So always we have a trivial symmetry, where we just don't do anything. We leave the picture as it is. This also goes under the name of identity or identity transformation. But then when we also have one non-trivial symmetry where we can reflect this picture across the vertical central line. And so if we do this, then we get back roughly the same picture. So we have two symmetries in this case, the identity one and the reflection across the vertical central line. So in this case, the group of symmetries is cyclic group of order 2. Okay. Then Islamic art also provides a rich source of highly symmetric objects. And here is a detail from Wazir Khan Mosque in Lahore. And we would like to find its symmetries. So what can we do here? So we can reflect this image for 60, 120, etc. degrees, or reflect, rotate, and then we can also reflect it. So we have 6 rotational symmetries, and we also have 6 reflection symmetries. So altogether we have 12 symmetries, and the group of symmetries is the integral group D6. So it can be generated by one rotation, for example, for 60 degrees, and one reflection. So this is a presentation of this group, but it's not really important for us at the moment. Then we come here at Lens, and so the central courtyard in the academic block is of special shape, so it's of octagonal shape, and we want to find its symmetries. So similar to the previous example, we have here, I don't know, is the green shares somewhere? Okay, so we still, so here we have the, again, rotational symmetries and reflection symmetries. So we have 8 rotational symmetries and 8 reflection symmetries. So the group of symmetries in this case is the integral group D8. Okay, and now, so what did we do? So we started with geometric object, and we found its symmetries. But now we would like to do a converse. So starting with a group, with an abstract group, can we realize it as a group of symmetries of an preferably geometric object? So our first step in this direction is the Cayley's theorem. So any group can be realized as the subgroup of its symmetries. But this second group is bigger than the first one. And in the case of finite groups, we can really realize our group as a group of symmetries of some polytope. Okay, so maybe let's look at some examples of not so abstract groups. So symmetric group on 4 elements, we can see as the symmetry group of tetrahedron. Then the product of the symmetric group on 4 elements and the cyclic group of order 2, we can see as the symmetry group of a cube and at the same time of an octahedron. And then the alternating group of A5, we can see as the symmetry group of icosahedron and dodecahedron. Okay, so we found symmetry groups of some geometric objects, and then we were also considering the inverse problem. And now we will go a step further. So we will associate a group to an object which is not necessarily, which doesn't necessarily have symmetries, but we will extract from these objects another objects which do allow symmetries. So the object that we will start with is a polynomial. So we start with a polynomial in one variable with coefficients in Q. So we assume that this is an irreducible polynomial of degree D. So because it is irreducible, we know that it doesn't have zeros in Q. And what we do, so we adjoin zeros to Q, and we obtain a bigger field. So in this case, here it's denoted by L, and it's also known as the splitting field of F. And now we will consider the automorphisms of this field. So this is a group, and every automorphism fixes Q. So then in particular, it also needs to, because F has coefficients in Q, so it needs to fix the set of roots of F. So this group is a subgroup of a symmetric group on the set of roots of F. And it's also called the Galois group of F. And so now an example. So we take this polynomial, So it's irreducible, and it has 3 roots. But if alpha is one of its roots, then we can express the other 2 in terms of the polynomials in alpha. So these exact expressions are not really important, just that we can express them in terms of polynomials in alpha. So what does this mean for L? So it means that when we adjoin alpha, we already have the other 2 roots. And then when we look for the automorphisms of L, so these automorphisms are determined by the image of alpha. And we know that any automorphism needs to preserve the set of roots of F. So then we have 3 possibilities. Either we send alpha back to itself, or we send it to alpha 2 or to alpha 3. And it turns out that in this case, the Galois group is equal to C3, to the cyclic group of order 3. So we see that this Galois group can be smaller than the symmetric group. Okay. And again, we will consider the converse, so the inverse group. So we ask whether any group can be realized, any finite group can be realized as a Galois group of some polynomial. So we are asking whether there exists a polynomial such that its Galois group is isomorphic to G. And so this is known as the inverse Galois problem. And actually, the answer to this question is not known. So it's an open question. But note that here we assume that the coefficients of F are in Q, so like the rational numbers. So if we allowed for the coefficients field to be any field, in this case, we could find such a polynomial whose Galois group would be equal to G. Okay. And now we go yet another step further, and we will go from the polynomial equations to more complicated equations, namely to differential equations. And there we will also find a group. We will associate to a differential equation a group which will act on its set of solutions. But in this case, the set of solutions will be infinite. Okay. And so this is the content of Hilbert's 21st problem. So Hilbert in 1900, he published a list of 23 problems. And the 21st one was the following. So show that there exists a linear differential equation of the Fuchsian class with given singular points and monodromic group. So let's try to decipher this a little bit. So what does it mean for a system of linear differential equations to be of Fuchsian type? So let's represent this system of linear differential equations in a matrix form. So here A of Z is n times n matrix of functions in Z. And we require that these functions are holomorphic on C bar. So what is C bar? C bar is C union infinity. Okay. Except that finitely many points, A1 up to A capital N, at which these functions have a pole of order 1.
who's available.
So this is the definition of a system of linear differential equations of group simplified. So that was the first thing that appeared in the formulation of the Hilbert's 21st graph. And then we also need to explain what monodrome is. So we assume that we have this system of linear differential equations and assume that it has singular points at A1 up to A capital N. Then we choose closed paths in the complement of these points. So closed path just means that it starts and ends at the same point. And then we take a basis of solutions, but these solutions we only know that they exist locally. So we take a basis of solutions in some neighborhood around gamma 0. And then we analytically continue them along gamma, and we denote the new solutions by gamma gamma 1 tilde up to gamma and y1 tilde up to yn tilde. Okay, so what does this mean, this analytic continuation? Okay, so I don't know if it's visible. So here we have our path gamma. See? And it starts here, but gamma of 0 is equal to gamma of 1. So it's a closed path. Okay. And now assume that, so as we said, we don't necessarily have global solutions to our system of linear differential equations, but we know that they exist locally. So we cover the gamma with some open neighborhoods. So these are these ovals where we have a basis of solutions. And now we start at gamma 0, and we assume that we have a basis of solution given by y1 up to y. Okay. And then on this second red oval, we have another basis of solutions. So we have basis of solutions given by A1 up to AN. And now what happens at the intersection? So at the intersection, we have two bases of solutions. So we have the solutions given by y's and the solutions given by a's. So they are both a basis of solutions, basis of an n-dimensional vector space. So we know that they are related by an invertible matrix. So they are related by an n by n invertible matrix. So y is rho 1 times a. And now we would like to define solutions on this red oval, which would agree with y on the intersection. So this is this y tilde, the analytic continuation of y also to the red open set. And so how can we define this? We can set y tilde to be equal to rho 1 times a. And then we see that on the intersection, indeed, this y tilde, functions y tilde are the same as the functions given by y. Okay. And then we can also we can continue this process. So on this next oval, we have another basis of solutions given by b's, and on the intersection, we can express them. We can express a's in terms of b's. So A is rho 2 times B, where rho 2 is an invertible n by n matrix. And we can define y tilde as the product of, so as rho 1, rho 2 times B, And we see that this y tilde coincides with this y tilde on the intersection. And now we can continue this process. And then when we come to this last open set, we can define y tilde. Oh, sorry, here it's, I apologize, H is missing here. Y tilde in such a way. But then we can also go back to the first open set. So what do we find then? We find that y tilde is this y tilde is the rho 1 up to rho 9 times y. Okay, so when we come back, y tilde is not necessarily equal to y. So what is the difference between them? So they differ by an invertible and by a matrix. So they are both bases of solutions on these open sets, but they might not be equal. Okay? And this is now how this composition of invertible matrices, which is also an invertible matrix, will give us the action. Okay, so we come back to this slide, and as said, we find out that the analytic continuations of y's, so y tildes, they're related to y's by an invertible and by n matrix. And so now we can then talk about the monodromy representation. So which group we do we choose? We choose the group of loops in the complement of singular points in C bar. So, and this loops up to the homotopy, and this is the fundamental group of that complement. Okay, and so what we do to any loop gamma, we associate rho gamma. And this is the monodromy representation. Okay, so what we have, which group did we associate to to a system of linear differential equations? We associated the fundamental group of the set, the fundamental group of the set of points in which this system of linear differential equations that doesn't have singular points, or on the complement of singular points. And then this group acts on the solutions by the monodromy representation. Okay. Okay, so let's look at an example. So we take this differential equation, which has two singular points, and then we take a loop. So this loop traces the unit circle, and then so what we need to do is we need to find a solution, a local solution. So what would be here a good candidate for a solution? So we could take the square root of that. But we need to be a little bit careful because we are in the complex plane. So we have complex numbers. So how can we define the square root of z? So if we take polar coordinates, so then we have the radius and the angle. So what we can do, so we can just take the square root of the radius and then half of the angle. But what's the problem with that? Okay, so this we cannot really define in a continuous way, because if we have an angle which is equal to 0, then half of the angle is 0. But we have the angle that is 2 pi, then half of it is pi. So what we need to do is we cover this loop gamma, we cover with 2 open sets. So here the green one and the red one. And on the green one, we choose so we represent Z with polar coordinates, but we choose phi from 0 to 2 pi in the open interval. And then on the green set, and in that case, we can just define the square root of Z in a continuous way. And then if we look at the green open set, there we choose phi from minus pi to pi. Okay? And in this case, we can then also define we can define a solution, just as we would do. Okay. And now what happens at the intersection? So at the intersection, we have two solutions. So we have y and we have a. And so on this intersection, on the red open set, phi is between pi and 2 pi. Okay? While on the green open set is between minus pi and 0. So they differ by 2 pi. And then when we take half of it, differs by pi. So this gives us that y is equal to minus a. Okay. And then, so in this case, y tilde is equal to minus a, while on this second intersection, we have there the phi's are the same on the green open set and on the red open set. So on this intersection, a is equal to y. So then when we come back, we find that y tilde is equal to minus y. So then the monodromy representation. So first, which group do we have? So we have the fundamental group of C bar without 0 and infinity, which is the same as C without 0. And so the fundamental group is just Z. And we can, and this pad gamma corresponds to 1 in Z. Okay, so then 1 maps to minus 1, and that's why k maps to 1 minus to the power k. So in this case, we get that monodromy representation. So now we come back to the problem. So to the Hilbert's 21st problem. So we start with some finite sets in C bar. So in C union infinity. And then we look at the fundamental group of the complement of this finite set in C bar. And as the input data, we also have one representation of this fundamental group. Or in other words, we have a group homomorphism from this fundamental group to some group of n times n invertible matrices for some n. So that's our input data. So some finite set of points in C bar, and then the representation of the fundamental group of the complement of this. Okay, and then the Hilbert's 21st problem asks whether there exists a system of linear differential equations of Fuchsian type with a monodromy representation equal to ρ. Okay. So to any system of linear differential equations, we can associate a monodromy representation, and now this Hilbert's 21st problem is the inverse problem. So we fix the monodromy representation, and then we ask whether this corresponds, we fix some representation, and then we ask whether this is a monodromy representation of some system of linear differential equations. Okay. So that's the problem. What progress has been made. So first solution was proposed already in 1908 by one of the first Slovenian mathematicians, Plem. But unfortunately, it turned out that his proof was not entirely correct. So that was found out by Ilyashenko in 1970. And then about 20 years later, a counterexample was found by Bolibruch. And then the problem transformed into classification of those representations that give the monodromy representations of differential equations of Fuchsian type. But among the algebraic geometers, the focus was more directed towards higher dimensions, but with a suitably rendered condition. So instead of Fuchsian type, one now requires regularity. So this means that in complex dimension 1, that on each punctured angular sector, the solutions are sufficiently bounded. So this also has an algebraic interpretation that generalizes to higher dimensions. And this definition of regular singularities was actually the cornerstone of the correspondence that we will see now. So this is the Riemann-Hilbert correspondence. So we start with a complex manifold, and then in this complex manifold we take a divisor. So that's a hypersurface. Okay, and then we have one-to-one correspondence between the systems of linear differential equations on X with regular singularities contained in D and the representations of the fundamental group of the complement of D in X. So this theorem was proved by a Belgian mathematician, Libre, and he's also a Fields medalist. Okay, so in our example, so what was X in our example was C bar, and D was this finite collection of points in a finite set of points in C bar, and this is a generalization to higher dimensions. So what we could also say is that here the topology on this on the right side, measured by the fundamental group, is somewhat determined by algebra or analysis, represented here by systems of linear differential equations. Okay. And so now we divert our story to mirror symmetry. Yes. So this is a hypersurface. So it's a sub. It's not necessarily a submanifold, but it's a subvariety of complex dimension 1 less than the dimension of X. So it's of complex if the X is of dimension n, this is of complex dimension n minus 1.
Hyperplanar.
It can be hyperplane arrangement, yes, but it can be more general. So it's usually the vanishing locus of some polynomial. Okay. So now, yes, we divert our story to mirror symmetry. So there we will encounter some representations, and we will try to associate to them systems of linear differential equations. Okay, so let me maybe first say a few words on mirror symmetry, very few words. So this is a theory that has its origins in physics, or more precisely in string theory. And their spaces have complex and also symplectic structures. And moreover, they come in mirror pairs. So in mirror pairs with a complex and symmetric symplectic structure interlaced. So if we have a mirror pair X and X naught, then the complex structure of X determined the symplectic structure on X naught, and vice versa. Okay. And now we fix X as a complex manifold. So we fix the complex structure on X. So this then fixes, with this we fix the symplectic structure on X naught. But then we still have a choice for complex structure. So we denote by this Kx the space of complex structures on X naught. And then mirror symmetry, or more precisely homological mirror symmetry, predicts that there is an action of the fundamental group of this space. So the fundamental group of this space provides some symmetries of X, but not necessarily geometric symmetries, but some hidden symmetries. Or more precisely, this fundamental group acts on some category naturally associated to X, which is called the derived category of X. And we will come back to this in a minute. And then, as a consequence of this, we get that the fundamental group of Kx also acts on the Grothendieck group of X, on the complexified Grothendieck group of X, which in our cases will be always a finite dimensional vector space. And it's this action that for which we will wonder to which system of differential equations it corresponds. Okay, so now we will say a little bit about the derived category. So this is somehow a gadget that contains a lot of information, cohomological information about X. So we assume that X is a complex manifold. And then first we look at the vector bundles on X. So these are families of vector spaces parameterized by X. So for every point in X, we have a vector space, and in a suitably coherent way. So a trivial example of a vector bundle, which is also called a trivial vector bundle, is just we take the product of C to the n times X. So then for every point in X, we have a vector space. Okay. And then to get the derived category of X, we need to take bounded complexes of vector bundles. So we need to have vector bundles, here V0, V1, etc. And then we also need to have maps between them. So we have D0 from V0 to V1, etc. And there is an extra condition that the compositum of consecutive maps is equal to 0. So what would be an example of a complex of vector bundles? So if we have a vector bundle that is a subbundle of another vector bundle, so V0 is a subbundle of V1, and then for V2 we take the quotient, then we have the following complex of vector bundles. So this is a very special complex of vector bundles, so-called short exact sequence. Okay. And then from the derived category of X, we can extract the Grothendieck group of X, which is defined in the following way. So we take the free group on the set of vector bundles on X. So this is this part. And then we need to quotient by some relations. So by which relations we quotient? So if you look at this example of a complex of vector bundles, we somehow see that V1 is built from V0 and V2. And so in the Grothendieck group, we require that V1 is equal to V0 plus V2. And so this is for all such sequences that we encountered in the example. For such complexes that we encountered in the example. Okay, so that was something about derived category. And now we look at an example that will be actually the running example for the rest of the talk. So we take for Y, we take the conifold. So how is this defined? So this is the vanishing locus in C to the 4 of this polynomial. Okay. And so this conifold is almost like a manifold. So all points are smooth except for the origin. And then we want to have complex manifold, so we want to remove this singularity. And so with X, we will denote some small resolution of Y. So there is also a combinatorial model for the conifold and its resolution. So we can represent Y as this cone over the square in R3. And then to get its resolution, X, we insert this extra diagonal hyperplane, or we divide the cone in two smaller cones. So this is a combinatorial model that comes from toric geometry. And then yet the third point of view to see this conifold. So we can look at the action of a one-dimensional torus on a four-dimensional vector space. And so this action we define in the following way. So an element T from the torus, it acts on the first coordinate by rescaling it by the T inverse, the same for the second coordinate, the third coordinate we scale with T, and also the fourth coordinate. And then there is a way to take the quotient. So what is the quotient? Quotient corresponds to the invariant ring for this action. And then to get X, we need to remove from C to the 4 some so-called bad points. So these are the points at which for which the first two coordinates are equal to 0. And then we again take the quotient. So, and now the physics heuristics tells us that this space of complex structure on the mirror of X, on X0, is equal to P1 without 3 points, or to C without 0 and 1. And the derived category of X, so we said all the bounded complexes of vector bundles on X, this embeds into another category. So the category of vector bundles on C to the 4. So here all bundles are trivial, but then we need to do some extra things. So we also need to consider this action of the one-dimensional torus. So we have only those vector bundles that also have an action of the one-dimensional torus. And also the maps between the vector bundles, they should respect the action. And so this image is generated by two trivial vector bundles. And on the first vector bundle, the action of the one-dimensional torus on C is trivial, while on the second one, an element T in the torus acts by rescaling X by Tx. Okay. So we have two trivial vector bundles, or two line bundles, but on the second one, we also have a non-trivial action of the torus. And then one can check that in this case, the fundamental group of Kx acts on the derived category of X. And then the Grothendieck group of X in this case is Z2. And in the basis given by these two vector bundles can be represented by the following matrices. Okay, and these matrices will also appear later on. And it's this point of view, so an action of a torus on a vector space that we will pursue. Why? Because in this case, the physics heuristics for Kx is rather reliable. But we will need to restrict to representations, to actions that are symmetric enough. So that's our general setting. So we have an n-dimensional torus acting on a d-dimensional vector space. And to get x, we first need to remove some bad points from the vector space, and then we take the quotient. So this is a similar thing as we did for the conic. And then in this case, physics heuristics tells us that Kx is the complement of a hypersurface in the torus. And this hypersurface is given by some so-called principal GKZ detector. So it's some object that has been well studied before. And then in the case that our representation is symmetric enough, so-called quasi-symmetric, then in this case, Kx has a especially nice form. So it's a complement of a hyperplane arrangement in logarithmic coordinates. So let's look back at the conifold. So in this case, as we said, Kx was C without 0 and 1. So if we take the logarithmic coordinates, so it means that we apply this to C without 0 and 1. So 1 divided by 2pi times log. And then we get that this is C without Z. So the complement of Z in C. And Z is indeed a hyperplane arrangement in C. It's an infinite hyperplane arrangement, but at least locally finite. And this is also what happens in a general symmetric enough situation. We always get a complement of a hyperplane arrangement. So why is this somewhat helpful? Because in this case, we have a very concrete combinatorial description of the fundamental group, which allowed Halpern, Meister, and Sam to show this homological mirror symmetry conjecture. So that in this setting, we have an action of the fundamental group of K of X on the derived category of X. And then, as said, this descends to the Grothendieck group of, so this can be also generalized to some more general reductive groups. But so what we will be interested in is that a set of this action restricts to an action on the Grothendieck complexified Grothendieck group of X. So this becomes a representation, finite dimensional representation of this fundamental group. And we will try to find which system of differential equations it corresponds. Okay. And so let's look again at the conifold. And we have a very known Gauss hypergeometric equation. So this is this differential equation, and its monodromy in a suitable basis can be described by the following three matrices. So if we restrict now, if we set the parameters A, B, and C equal to 0, we get the same matrices as we have seen before. And so what does this mean? Is that the fundamental group of X on the K0 of X, so that this action corresponds to, by Riemann-Hilbert correspondence, to the Gauss hypergeometric equation with parameters A, B, and C equal to 0. How much time I still have? So it's over. Okay.
But we started late. You can take 2 more minutes.
Okay. So then let me just say that there is also an so this hypergeometric Gauss hypergeometric equation has a solution given by hypergeometric function. And there is also a generalization of hypergeometric function to higher dimension. And then so to the higher dimension, and then Kirchhoff, Brano, and Zelewinsky, they constructed a hypergeometric system of differential equations in such a way, they designed it in such a way that these hypergeometric functions would be its solutions. Hypergeometric series would be its solutions. And that's what happens in the general case. So this action that's predicted by homological mirror symmetry corresponds to the monodromy of a GKZ hypergeometric system. So sorry for going over time, and shukriya.
Are there any questions or on your?